Hi, this is Kan-Lin speaking. I'm from National United University, Department of Energy Engineering. In this unit, we are talking about renewable energies. Because the energy storage or microgrid is because renewable energy and stable power output. That's why they become more popular. In the renewable energy, in this section or the unit, we'll talk about including the pump hydro or the hydropower station and wind turbine and photovoltaic. These three major renewable energy. Because those renewable energy maybe depends on weather, so you need a battery or the energy storage to buffer to make a power output more manageable. First, we talk about pump hydro. According to the EPRI, Electric Power Research Institute in the United States, they report the pump hydro storage accounted for more than 99% of bulk storage capacity worldwide. The pump hydro storage is a large capacity energy storage for the grid scale at the present time. I think the basic principle everybody knows, but anyway, I just repeat that. It's the store the electricity as a potential energy. They use the upper reservoir to store the water, a huge body of water. When they need electricity, then the water was released from the upper reservoir, goes to the lower reservoir through a power generator to the lower reservoir here, and then generate the electricity. But when you got excessive electricity, extra electricity, then you can feed the electricity back to the pump. The generator become pump, and then will pump the water from the lower reservoir to upper reservoir, and then store in form of potential energy. In the energy storage efficiency, somewhere around 70 to 80%, because of mechanical loss and water evaporation during the in the reservoir. But also in a newer pump storage, they also consider the environmental and biological balance. For instance, like usually those pump hydro was built along the river. They cut the river and then bypass the water through the generator. So traditional the fish flows through the river, maybe get interrupted or get sucked into the power generator or the pump. So to avoid that, usually had a protection grid or mesh to avoid the fish accidentally be sucked into the power generator. And inside the power generator or pump, the turbine is made of environmental friendly, maybe coated with a plastic or Teflon and without any sharp object, so the fish even get sucked into will not be seriously injured. And then they also build some bypass so the fish can flow through the river without any interrupt. So all this newer power pump hydro not only consider high efficiency, but also environmental, biological friendly. The same machine, they can generate electricity, we call the generator, or they become the motor, they can pump the water from the lower reservoir to upper reservoir. I use a model which I took from the power pump hydro station, and so they can cut section, probably more easy to describe that. This is the motor or the power generator over here, and then in front is connected with a pump or turbine. Is it called pump or turbine depends on you want to pump the water upward, or from the upward the water will push the turbine to generate electricity. So one device has two names, depends on its function. And this is a close lookup for the turbine or the pump. It rotates in one direction. Depends on your power generator, or acting as a pump. The specification, typical specification is given by this table. You can see the generator output is around 300 million volt amp, or the motor input is 283 megawatt, or 283,000 kilowatt, something like that. They are very close, and for the turbine output is 275 megawatt, or 275,000 kilowatt. The watt turbine or pump is a very close match with the generator, not bigger, no less. The maximum water drop, effective water drop, is 400 meter, and the maximum flow rate is 82 second meter cube. So in this case, actually we can calculate how much the power output by the from the water drop times the flow rate. We know how much potential energy maximum can be released theoretically, and then you can calculate the turbine output or the generator output. The maximum lift is how much the pump can pump the water, how high the pump can pump the water up. This maximum is 410 meter. And then in this power station, the upper reservoir, the lower reservoir, the elevator difference is somewhere around 370 or 300 meter. So it's within the specification of the pump. So there's no problem to pump the water from lower reservoir to upper reservoir. And then the max pump rate is close to the maximum flow rate downward. This is the only large size reservoir or the pump station in Taiwan, central Taiwan. Samu Lake is the upper reservoir, is the elevation is 748 meter high. And the lower reservoir, there's two lower reservoirs. One is the Minghu, one is Mintan. The elevation is 448 and 373 meter respectively. So you can see, so those far within their pump specification, 410 meter high. The elevation difference is somewhere around 300 meter or to 370 meter difference. This is the upper reservoir photo, and this is the lower reservoir photo. You can see for safety, most tourist attraction is on the upper reservoir. They call it Samu Lake. And usually in the battery, for the energy storage, mostly for the battery, we'll talk about the energy density. That means how much weight or how much space need for batteries to store a specific energy. But not too many people talk about the pump hydro. We just do a experimental calculation, see how it will come out. For the pump hydro, actually the store is a potential energy, PE, equal to MGH. The M is the mass of the water, and then G is a gravitational constant. It's 9.805 meters second square, and then the height is a elevation difference of the upper reservoir and the lower reservoir. Let's consider a experiment. We had 1,000 kilogram of water. That means 1 ton of water, or 1,000 liter, 1 cubic meter water drop from 100 meters above, drop to the ground. And then we'll convert all the potential energy into electricity, 100%. How much electricity will be generated? We can calculate by this. Then you can see the M equal to 100 kilogram times the gravitational constant 9.8, and then times the height 100 meters. Then we got 274 watt hour, or 0.274 kilowatt hour. 1 watt hour equal to 3,600 joule. So this is the energy conversion unit conversion. So we know in this experiment we can get 0.274 kilowatt hour electricity by running 1,000 kilogram of water from the top 100 meter drop to the ground. Now we're going to calculate the energy density. The energy density we can base on weight or based on volume. The weight is 1,000 kilogram, but the volume we had to consider is 2,000 liters. Although because there's an upper reservoir and lower reservoir, so we need both reservoirs in order for this operation be feasible. So we need a 2,000 liter space. So we do the calculation. Then the gravimetric energy density is 0.274 watt hour per kilogram, or the volumetric energy density is 0.137 watt hour per liter. So, is that good or bad, the energy density? We compare this number with conventional battery, such as lead acid battery and the lithium-ion battery. The lead acid battery is considered the lowest energy density among all the batteries. Then the energy density for lead acid battery is somewhere around 20 to 50 watt hour per kilogram. It's about 100 times higher than pumped hydro. For the lithium-ion battery, it's 200 to 400 watt hour per kilogram. It's more than 1,000 times than the pumped hydro. So you can see the pumped hydro energy density is much lower. But everybody actually not care about that, because usually in the tours, in the natural environment, and it's pretty, and also is need a big body of water, but it doesn't matter because usually it's far out west, far out in a remote area. You cannot do this in a city, in a metropolitan city, because the land space is limited. Then you really need a battery to do the energy storage rather than the pump hydro. The pump hydro is good for the central energy storage, but not for distributed energy storage. For instance, you're going to build it in your downtown, your basement, that will be impossible. This figure just plot the energy density on the y-axis against different energy storage system. This one is a pump hydro. You can see it's the lowest one. And then in the middle is an old conventional battery, like lead acid, nickel metal hydride, lithium ion, or even zinc air. For the zinc air in this plot is only for the primary battery. But the lead acid, nickel metal hydride, or lithium ion battery is secondary battery, can be used as a storage. You can see they are much higher than the pump hydro. Lithium ion battery is about 10 times higher than the lead acid battery. But in this scale, you don't see it because this is a log scale. So even small distance mean a lot. Then the third section is a metal air battery. They including zinc air, magnesium air, aluminum, and the lithium air battery. The theoretical energy density is much higher than conventional battery. But so far they're not commercialized because there's a 2 point they cannot overcome, at least at the present time. First, the power release from those batteries is very small. They only can release very small power rate as compared to conventional battery. So that's one drawback. Secondly, so far that's the problem to store the energy efficiently. That's a problem for right now, and need to do a lot of research to overcome the storage problem. The last one is a portable fuel cell. The last column. Usually, plot over here is a direct methanol fuel cell. But the direct methanol fuel cell can be used as a power generator. It cannot be store energy, at least at the present time. So just plot here for comparison. So the DMFC, direct methanol fuel cell, indeed had a very high energy density, both theoretically. I plot the square over here is right now the commercial available energy density somewhere there. The circle one is the means theoretical energy density. So far we've been talking about the pump hydro, the basic component, operating principle, and the energy density. Compare as other batteries. Now we do some exercise. Let's consider how much watt by volume or by weight will be needed to store 1 megawatt hour electricity. That probably for our university maybe 1 hour, half hour energy storage. Assume the upper-lower reservoir height difference is about 30 meters, somewhere around a 9 to 10 storage height. The conversion efficiency is 70%. The equation is a PE equal to MGES. You can substitute and then do the number crunch. Over here, I assume if you use a 5,000 kilogram, the water tank, one in the roof and the other one stored on the basement of the building, how many water tower or the water tank you need to store 1 megawatt hour electricity?